In this video, we're going to give an overview of the camera placement generative design workflow for Revit. In this case, we're placing a camera object around a room based on optimization criteria. This is a multi-objective optimization that's optimizing for a camera view of the entire room and how many doors the camera can see as well. This is made with MEP consultants in mind, so it is geared to work with linked models, so we'll get into that a little bit as well. With that in mind, we'll open up our Revit sample model. So in the sample model, we're in Revit 22, we have the advanced sample project linked in. I have it cropped down to the room that I know I want to work on. Within Dynamo, we have a few things going on. We have an input section. Within this input section, we have the ability to select a room from a link. We select the room in a floor plan view, and in this case, this node is a custom node from Rhythm. Selecting elements from links isn't directly possible with out-of-the-box Dynamo, so you have to use a custom node for this. Additional input types are the room perimeter location. This is the location along that top polyline that we see of where the camera will get placed, the up-down angle of the camera, and the left-right angle of the camera as well. If I scroll to the right here on this left-right angle and hit run, we'll see that view get updated in the background. For the visibility, this is using a custom package called VASA, which we'll link below, that does a lot of pathfinding operations, visibility operations, and more. It's a voxel-based package, so it does it in a 3D way. Other great use cases of this package would include pathfinding for MEP, or using these same visibility cones to lay out lighting or sprinklers as well. Other optional inputs include camera horizontal field of view and camera vertical field of view. These vary based on your manufacturer of your camera, so that's why they're in here as an optional input. This graph is made to work in an imperial file, but if you have a metric file, you can convert it to a metric operation with this true and false value. In addition to that input, we have the mounting height of the camera around the room. You can obtain this value automatically from the Revit model based on how tall the room is, but it's a little bit easier just to specify this based on how high we know we can mount the camera. As you can see, we have all of our visibility in place, and you can see the occlusion happening with these table objects and these columns. VASA is really cool because it runs very quickly for these kind of calculations in a 3D manner, and that made it the perfect candidate for this kind of operation. In addition to this, we have feedback to our user in the way of text. So we give them how visible is the space and how many doors can we see. That's another preview that we have built into the graph in these blue sections. So any of these blue sections indicate visibility operations to give the user feedback. And that's pretty typical from all the graphs that we've used previously as well. Our fitness functions are included in these orange portions of the graph. So we have the percentage of the room that's visible, and we have if it sees all of the doors. Once again, this is a multi-objective optimization, so we have two criteria that we're optimizing against. For a deeper breakdown of this graph, the blog post linked below has each section summarized quite a bit. In the event that you want to learn from this graph, there are notes and groups throughout the entire graph though for you to be able to investigate what it's doing. With all of that in mind, running optimization algorithms on a Dynamo graph is really great. The end result needs to work for users within Revit though. This orange section does that. At this point, we place a family that is a security camera that has parameters that can be set as well. This gate node prevents it from being placed until the optimization is complete. We have our pitch angle and our yaw angle. Pitch is up and down, yaw is left and right. And those are assigned right within a family that's included in the dataset linked below. So we have a generic camera family that has that pitch. Right now it's at 90, but if we change it to 45, we can kind of see how that starts to interact with our model. These parameters are all settable, and we are setting them with the generative design tool. All right, with that complete, we'll go ahead and save our graph, and we'll open it in generative design. In Revit, if we navigate to the Manage tab, we can navigate to the Create Study panel. By default, Generative Design will load all the graphs in our sample workflows folder. I went ahead and copied the sample workflow linked below into this folder. As a reminder, you can add more folders to this section if you'd like. I tend to use the out-of-the-box one for this because I work on a network path, and we're not able to map to a network path at this time. I'll go ahead and click on this workflow, and we'll see that we have a few options available to us. At this point, we need to select a room from our link. As mentioned previously, we need to navigate to a plan view, zoom into a room, and pick the room element. This selection will let you pick other elements, so you just need to be specific to pick a room. Now we have our room selected. We want to allow Generative Design to run around the room from 0 to 1, so the whole perimeter of the room. We want to allow it to change the up-down angle of the camera, the left-right angle of the camera as well. Our metric units option, we're just going to leave that tied to false. The mounting height, we'll leave it at 8.5 feet. This is an Imperial project. And we want to maximize the percent of the room visible. We want it to be able to see the whole room if possible. And we also want to maximize the exits in the view. Ideally, we'd see all of the exits within the room with that one camera. So we'll maximize that as well. These are all default values saved inside of the sample file, so keep that in mind. You can always save default settings in the ellipses button in the Define Study dialog. Our population size is 20, and the generations are 20 as well. With that in mind, we can go ahead and click on Generate to generate some results. And we'll let it run, and we'll cut back in whenever the results are complete. Once Generative Design is complete, it ran through a whole lot of iterations here, we will have our optimized result. As you can see, in this specific room, we have the ability to get 65% visibility and both doors visible. Both doors being visible is probably the more important criteria in this use case, but it is pretty neat to see both of them get optimized in that way. We can also zoom in and see how our results look in this preview window. Keep in mind, at this time, VASA does not display the color in the Generative Design viewport the same as it does in the Dynamo window. This is a known issue, and they're looking at it at this time. So we can kind of pan around and see kind of how those sightlines work, which is pretty interesting. Once we're done taking a look at the results, we can go ahead and create our camera object in Revit. So I'll just kind of tile my window a bit here. We'll see that my generic models, I have an override on those objects so we can see it easily. Let's go ahead and click Create Revit Elements in the Generative Design window. At this time, Generative Design is now opening that gate node in the background to create our object type in Revit with the parameter set. We'll go ahead and let this run and we'll take a look. Alright, and as you can see, we have a camera object placed. It's over here in the corner of the room. It's angled correctly now. It's highlighted pink, and we can kind of see how that angle works to capture 65% of the room and both doors. Really, really interesting stuff here. So we now have that set within our model, and we have that being tied right in. Further expansions on this graph could be adding a camera view in Revit with the nodes available in out-of-the-box Dynamo that have all of those parameters set as well. That'd be a really interesting use case to actually create axonometric views that mimic the camera view as well. With that in mind, I encourage you to download this file, take a look at it, try some of the other optimization criteria or the other study types for this as well, and see what kind of results you can get. All in all, this example shows a way of using a package that doesn't seem like it's related to MEP to do really neat things, so I highly encourage you to check out the VASA package, try out these files, and let us know what you think.